This is my program that I've written out. So I find my x to be ranging from negative pi to positive pi in steps of 0.02 pi. Okay, that's line number 5. Then all this whole thing, okay, this part here is to find the function value, is to find this guy here, this one. So that is my piecewise defined function, right? Okay, then from lines 12 to 15 is to find this sum, but the n is only 3. That means 3 terms only, n equals to 1, 2, and 3. The next one, S2, sorry, that is S2, S2, okay. I wonder where is S1, never mind. S3, oh, S2 is that term. S3 is 1 to 5. Okay, I know why it's S2, because it's actually only 2 non-zero terms. Then S15 is 1 to 29. Okay, so I can't go to infinity, I have to stop somewhere. So I plot, after finding this, because there is a 2 over pi which is constant, I take it out of the sum. Okay, so then I multiply by 2 over pi for each one of these, and let's see what happens when I run this. Okay, you see the 3 figures. This is figure 1. I made them a bit smaller and put it side by side for you to see. This is with more terms, and this is with even more terms. I hope I can squeeze it in. Alright. Okay, you can see on your screen, right? The 3 of them. The first picture, this one here, the one on the left, this one is using only a few terms. Let's say 2 terms, something like that. And the next one I use more term, and the next one I use about 30 terms. So you can see that it's oscillatory, but it sort of represents the approximate this function here, right? This function here. I did not remove this line here. Actually, this line shouldn't be there, so it shouldn't be continuous. This line here for the f of x should not be there, but we can fix it if we want to. But I just a bit lazy. I just put it in. So you can see that this is my green line is the Fourier series. This one here, we're using more terms, and when I use a larger number of terms, you can see it represents it this way. Okay, so this is correct. We verify it. Okay, we have time for one more example before we which of course I'm not going to solve the whole thing, but just to demonstrate to you also how this can be done. So the first part is to sketch the graph of this function first, and then find the Fourier series of the function. So can you try and sketch the graph? How does your graph look like? Okay. Here you should get something like this, right? The gradient is always 1. Sorry, this doesn't quite look like 1 on this side, but it should look something like this. So you get all these lines like this, right? So do you know the name of this Anyone knows what do you call this particular function? It's called sawtooth function because it looks like the teeth of the saw, right? Saw, okay? It's not really a name, but then that's how people call it, right? Sawtooth function. So how do we find the Fourier series? So the first part is that we have already sketched the graph. Okay, you see, you can do it this way. Your f of x equals to s plus pi on this part here. So in this interval, you can sketch it already. And then you know that it's f of x plus 2 pi equals to f of x. That means it's actually periodic with a pair of 2 pi, 2 pi, 2 pi. Right? So it's like this, and the other side. So that's how you get this graph. Now then, the question now is to find the Fourier series of this function. So the question we always ask is that, okay, to make our life easier, we try and see whether it's odd function or even function, right? So is it odd or even or neither? Huh? Neither.
But can we like translate?
Translate?
No.
How?
That means you find the expression.
Okay, that's a good idea. You translate. How do you translate? You want to subtract by pi. So instead of, so your idea would. So because of its periodicity, we only need to focus on this side, huh? Okay. So can you see that? Well, we can do this. We can do fx equals to x plus pi. And we break it up into two parts. Okay, so we have say f1 equals, and then we have f2 possible. So then you can find the Fourier series for this, and you can find the Fourier series for that one, and they are all sums, right? So you add them together. That may be easier. I don't know whether you can try your other way. So I will not complete this. I leave this as a kind of challenge for you to complete this, and of course, eventually, when you do this, what you can do is to write a MATLAB program to verify whatever that you have found, just as I have done the other way. Okay, so whether you can do that doesn't matter, because later on the MATLAB programs, even for example 3, will be posted for you, so you can check from there. Okay, so eventually when you run your program, what you will see, if your program is correct, if you plot this, it's like this. You plot the original function f of x is like that, and when you plot your, what you will see will be a function that looks, maybe I use my pointer to show. Okay, you have this, you will see something like this: oscillate, 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 then oscillate, oscillate, then oscillate. Okay, oscillate. That is your series. Okay, and the more terms you use, the smaller the oscillation here, and then suddenly very big oscillation there, and then small, and then. So in other words, if I want to mess up, okay, like I mess up my picture, my nicely drawn picture. Okay, it will be like that. Okay, you see this sharp oscillation going up and down, and then after that very small over here. If you use high number of terms, like that, right, and like that. So there is actually a name for this particular phenomenon. Okay, it's called Gibbs phenomenon. Okay, and some of these things are actually quite hard to explain why they happen. This one, of course, can be explained. Okay, so what we have done so far is to introduce partial differential equation, and then introduce Fourier series. At this point, you still do not know why am I doing Fourier series when I'm supposed to be doing partial differential equations, right? You want to know, come back after the break. You have a break now.